Hello, AP Chemistry students. We're now at section 3.11 and 3.12. I've combined these two into one presentation because they're both about how light interacts with matter. And we're going to be talking about spectroscopy, the electromagnetic spectrum, and the photoelectric effect. So our learning objectives are to explain the relationship between a region of the electromagnetic spectrum and the types of molecular or electronic transitions associated with that region, and then to explain the properties of an absorbed or emitted photon in relationship to an electronic transition in an atom or molecule. So basically everything we know about atomic scale matter, about atoms and molecules, we've been able to infer through its interaction with light. So light is made up of photons. Photons are the name of the particles of light. And we describe them as being quantums of electromagnetic radiation. A quantum is a fancy word for saying a discrete quantity, like a specific amount of energy. And a photon has properties of both a particle and a wave. So we can visualize it as a single point in space that is moving. And then we can also visualize it as a wave, something that sort of vibrates through space and has properties of a wave, which we'll talk about in a moment. We also know that the color of light is correlated to these wave effects, and that the amount of energy they carry can affect the color of that light. So let's talk about waves. So a wave has classically three important properties to it: the wavelength, the frequency, and the amplitude. And all three of these are going to help us talk about the properties of light. I should add an Oxford comma there. Okay. Um, so the wavelength, which is represented by the Greek letter lambda, represents the distance between wave peaks or troughs, and this is usually in meters or some sort of form of length. So if we look at this wave here, we can measure the wavelength as being the peak here to the peak here, or the trough here to the trough here. Basically, the space between the peaks of the individual wave motions. The other thing that we talk about in terms of the wave properties is the frequency, which is represented by the Greek letter nu, which kind of looks like a V. And these are the number of waves per second. And we usually measure those in units of per second or hertz. These are the same thing. If you said something happens 1 time per second, it has a frequency of 1 hertz. And if we were to look at this here, say we have this time scale of 1 second here, we could see that the wave is happening twice. So its frequency would be 2 times per second, or 2 hertz. And the amplitude of the wave, which is represented here, it's like how much it's waving by. And this is affected by the number of constructively combining waves. It's basically the intensity of the wave. And what we know based off of these properties and their sort of spatial relationship to each other is that the higher the energy, the higher the frequency, and the shorter the wavelength. So imagine this wave here. It's happening twice in a second. If we were to visualize a wave that had more energy, we might imagine something more chaotic, something that is waving faster. So that is why the frequency is higher in a higher energy wave. We can imagine this waving several more times per second, and that would be a higher frequency and higher energy. And also, if those waves are going to be happening more per second, we can visualize them as being closer together in space, which means they're also going to have a shorter wavelength. And this relationship is very important, and we'll talk about the sort of quantitative part of it later. The amplitude, which I described as being the sort of the height of the waves, the magnitude of the waves, this basically comes from having more particles that are sort of combining and waving together. So if we were going to talk about light waves, higher amplitude would be more brightness. So if you think about like a dim light, or maybe like one of those lights that has like a slider on it, you start at dim and then you go to high, you're increasing the amplitude of the waves, but you're not actually changing the frequency or the energy of those waves. There's just more of them happening all at once. So if we're going to talk about the math involved with light and light waves, we're going to look at the equation here. So this is an equation that says lambda nu is equal to c. So the wavelength of the light times the frequency of the light is equal to the speed of light. And the speed of light is a universal constant. Light is the fastest thing in the universe, and it goes exactly 2.998 times 10 to the 8 meters per second. And this value kind of relates the amount of time something is waving to the distance between the individual waves. The product of these two will always equal the same value. So this helps us know one if we know the other. If we know the frequency of light, we can calculate its wavelength and vice versa. So let's say we wanted to know what the frequency in hertz of a photon of light with a wavelength of 2.0 times 10 to the negative 7 meters. Well, to solve that, I would plug it into the equation and solve for the frequency, which is nu, this like V looking symbol. So I'll have nu is equal to the speed of light divided by the wavelength. And we can make sure that our units all agree. The value for the speed of light is in meters per second. The value of the wavelength is in meters. So the meters are going to get canceled out, and then we're going to have 1 over seconds or per second or hertz. So we divide these two values, and we end up with 1.499 times 10 to the 15 inverse seconds, or 10 to the 15 hertz. And you can see here we had a pretty short wavelength, which means we're going to have a very, very high frequency. Remember, those two things are inversely related. So another really important equation that relates to the frequency of light is this one, where we have E is equal to h nu. So E represents the energy of the light, which is usually measured in joules, or capital J is the symbol for it, is equal to h, which is something called Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. Both this and the speed of light constant, you don't need to memorize. They will be on the equation sheet that is in the reference folder for the class. So the product of Planck's constant and the frequency will give us the energy of the light. So say we had that photon from the previous example that had the, what was it? The wavelength of 2.0 times 10 to the negative 7. We were able to convert that into inverse seconds, or hertz, and then plug that into this equation to calculate the energy. Since we have joules times seconds times inverse seconds, seconds are going to get canceled out. We're going to get units of joules. And then when we do the math, we end up with an energy value of 9.9 times 10 to the negative 19 joules. This might seem like a low amount of energy. It's a really small times 10 to the negative value. But if you're imagining a single light particle, this is something that basically has no mass at all, that's a pretty decent amount of energy. So from all this, we can determine that energy is directly proportional to frequency, and if we increase the energy, we increase the frequency, and vice versa. So there's one more equation that we can get out of this by combining the two equations we already looked at. So if we solve them both for nu, we can come up with an equation that relates the frequency to the energy, which is going to be pretty important in the coming slides. So if we solve them both for nu, which is a variable that they both have in common, we could say nu is equal to the speed of light divided by the frequency, and then that nu is also equal to energy divided by Planck's constant. And then we'll have C over lambda is equal to energy over Planck's constant, and we could solve for E. So that tells us that the energy of a particle of light is going to be equal to these two constants multiplied by each other, Planck's constant and the speed of light, divided by the wavelength. And from this, we see that energy is inversely proportional to wavelength. So the smaller the wavelength, the higher the energy. But that makes sense because you can think about a high energy wave having really small, really frequently happening waves. That means that the distance between the peaks of the wave are going to be very small. So let's use this to solve a problem. So what is the energy of a blue photon with a wavelength of 495 nanometers? So we want to calculate the energy. H and C are both constants, so we can get those values from the table or the reference sheet. So those will be constant in most of these wavelength to energy calculations. And then we have lambda here, which is the wavelength. It's given to us in nanometers, but if we want the math to work out right, the units need to agree. So we could see here that we have units of meters in our speed of light. So the frequency that we plug into this equation is also going to have to be in meters. And we know that 1 nanometer is equal to 1 billionth of a meter, or that 1 billion 10 to the 9 nanometers are in 1 meter. So we can use that to convert. So we have our two constants multiplied by each other, and then our value in meters from 495 nanometers is now going to be 4.95 times 10 to the 7 meters. And we can see here that the seconds are going to get canceled out and the meters are going to get canceled out. And then we end up with just units of joules. So we end up with a final value of 4.01 times 10 to the negative 19 joules associated with the energy of a blue photon. So speaking of blue photons, all of the different types of wavelengths of light that you can get, all of the different values in either meters or nanometers. There's sort of a wide range of possible of wavelengths, and these are collectively known as the electromagnetic spectrum. So you can see here we have our low energy waves that are happening very slowly, and they get faster and faster and more energetic, and then we end up with really, really short wavelengths. So the regions associated with these are radio and microwave, and kind of the smaller or the longer wavelength slash low frequency waves. And then in the middle is visible light, which is the light that we can see with our eyes. And that gets into ultraviolet, X-rays, and gamma rays in increasing amount of energy. Here's just some visual references of things that are about the same size as the waves. So radio waves are like as big as buildings, and gamma rays are as small as atomic nuclei. So it's a very wide range of wavelengths. And like I said earlier, the visible light, that's the light that we can see with our eyes as human beings. And this makes up such a small portion of the electromagnetic spectrum. You can see here, it's just this tiny little bit in the middle. And this is a logarithmic scale, so it's a little bit exaggerated. We can see very little with our human eyes. In fact, it's a specific region of wavelengths between 390 and 700 nanometers. So there's only a range of about 300 and something nanometers that we can directly see with our eyes. Also corresponds to frequencies of 430 to 770 terahertz. And here you can see that there are different wavelengths associated with different colors. So at the higher energy, the shorter wavelength part of the spectrum, we have the ultraviolet and blue light, which goes into green and then yellow and then orange and red. If you remember the acronym Roy G. Biv, that tells us the order that they appear in from lowest energy to highest energy. So red, orange, yellow, green, indigo, blue. Blue, indigo, violet. I had it mixed up. Whoops. Okay. So depending on the wavelength of light, we see that different regions of this spectrum have different effects when they come in contact with matter, when they come in contact with atoms and molecules. And this is totally based off of the amount of energy contained within them, because the radio, microwaves, and infrared are going to be lower energy, and then the visible, ultraviolet, X-rays, and gamma rays are going to be higher energy, and that's going to affect how both the atoms and the molecules themselves vibrate as they absorb that energy, and then how the electrons within the atoms are going to move. And specific substances, depending on what they're made of, what the atoms and the molecules are, and what their bonding properties are, will be able to absorb specific wavelengths with specific quantums of energy. I'm going to talk a little bit about that later. But and the wavelengths that aren't these specific ones are not going to be absorbed, no matter how energetic, and they'll just pass right through. And this is called transmission. So light waves can be absorbed by a substance, or they could be transmitted. They can go right through it, and only specific types of energy can get through based off of the properties of that substance. And I'll explain a bit more about that in a bit. So we can use light to probe the physical properties of matter, basically looking at if the light is absorbed or transmitted using a process called spectroscopy. And we use a spectroscope or a spectrophotometer, which is a fancy instrument that can detect which specific wavelengths of light are either absorbed or which can pass through, which are transmitted. And the general setup is usually you have some light source that shoots a high energy beam of a bunch of different types of light all mixed together. If you ever think about white light is actually sort of a mixture of the whole spectrum. So there's like a bunch of different colors of light contained within in white light. And then it passes through a dispersion device, something like a prism, which separates out all the individual wavelengths into like a rainbow or a spectrum of light. And then that's going to go through what's called a monochromator, which is a device that separates out the individual light and only lets one of them pass at a time. It usually rotates through all of the colors to collect a full spectrum. And then you'll see all of these different wavelengths of light passing through a certain sample. And whether that light is absorbed or transmitted will then result in a value at the detector of the amount of absorption. So depending on the type of light, the wavelength of the light, the energy of the light, it's going to have different effects on matter. So microwaves, which have wavelengths around 10 to the negative 2 to 10 to the negative 3 from hundredths and thousandths of meters, these usually affect the molecular rotation of a substance when it's absorbed. Here you can see what looks like a carbon dioxide molecule. And this is showing the rotational motion caused by microwaves. So it can either rotate in this axis or in this axis you can see here. And this is usually this specific energy of light that causes this sort of motion in molecules. And infrared waves, which are around 10 to the negative 3 to 10 to the negative 7 meters, these affect the molecular vibrations. And what I mean by vibrations is the movement of the bonds themselves. They can sort of bend up and down. The lengths of them can sort of stretch either symmetrically or asymmetrically, kind of stretching at the same time or stretching at different times. And then the visible and UV parts of the spectrum, which is in a much smaller region from basically 100 to 700 nanometers, which is 1 times 10 to the negative 7 to 7 times 10 to the negative 7 meters. And sometimes the high energy IR waves, which are from 700 nanometers into the thousands of nanometers, these affect the electron transitions. So what that means is if you think about a Bohr model of an atom, or you think about the electrons that are in all of their different orbitals and subshells that all correspond to specific amounts of energy, if you were to hit an atom with a photon that was able to be absorbed by that atom, the electrons in those orbitals can get excited. And when they get excited, they move from the orbital that they're in to an unoccupied higher orbital. And this involves a certain amount of energy because if you're moving to a higher energy orbital, you're moving farther away from the nucleus, and you're going to need some energy to overcome the Coulombic force of attraction from the nucleus. So the farther you're moving, the bigger the jump of energy levels of your electrons, the more energy is going to be required to do so. So you can see here, this is a visible spectrum, and you can see here that there are black lines. These correspond to wavelengths that are not being transmitted. So you can imagine this is what the detector is seeing, and all of the colors that the detector sees are all of the colors that pass through the atom that are transmitted through the atom and not absorbed by them. And then where all these black lines are, they tell us the exact wavelengths or the exact quantums of energy that are required to promote electrons from lower orbitals to higher orbitals. We know that there are specific energy differences between energy levels, which means a specific amount of energy is required to get the electron to move, say, from the second energy level to the third energy level. And no other type of energy will do. If we have slightly less energy, it's not going to work. If we have slightly more energy, it's not going to work. You can think about it in terms of rungs on a ladder. They need to be in the exact spaces or the exact differences between the levels in order for it to work correctly. So here we can see that this red line is corresponding to a jump from the second level to the third level. This blue line is from the second to the fourth. And you can see here that the energy of the light is the shorter wavelengths in the blue and purple region are going to be associated with bigger jumps because there is more energy required to overcome that Coulombic force and get farther away from the nucleus. Let's see here. I kind of already explained this. All right. So the absorption wavelengths, as I was saying, tell us the specific quanta of energy required to promote electrons to higher energy levels. So this is an example for a hydrogen atom. We could see that the transition from the first level to the second level is going to require light with a wavelength of 122 nanometers, which we can use the equation from before to convert to joules, which will be on the scale of 1.628 times 10 to the negative 18 joules. And then from 3 to 4, this is a much bigger, a much longer wavelength, corresponding to not a much lower, but a significantly lower amount of energy. And based on this, we say that the energy levels in an atom are quantized. So why I keep saying quanta and quantum and quantized, these all refer to just specific amount of energy. The energy levels in an atom are always going to be, or for a specific atom, say a hydrogen atom, is going to have specific differences in energy levels. That is always the same. But for different elements, it's going to be different amounts of energy between their energy levels, depending on all of the Coulombic forces that are involved in that atom. And that's convenient because then that gives us a unique spectrum for every element. Everything's going to interact with light in a different way. And we can use that light to then probe more information about specific substances. Also, one quick thing, sort of related, is the energy levels. The farther you get away from the nucleus, the closer and closer they get to each other. So at a certain point, we end up forming like a continuum where all of these energy levels are sort of overlapping with each other. And we already saw examples of that between like the 3D and 4S subshells where electrons were able to move between them pretty freely because their energy levels are so close to each other. And at a certain point, we get this like continuum, this like band of energy levels that are all overlapping. And if we're able to get a little bit of energy to go slightly beyond that, that's when we get to the ionization energy. Because once it's past the sort of band of energy levels that are all kind of clumping together, then we've achieved enough energy to escape the atom completely. There are no shells at that point that we can occupy, and the electron is able to just leave the atom completely. It's no longer going to be attracted to the Coulombic forces of the nucleus. And the process of doing this is called the photoelectric effect. We already talked a bit about this when we were talking about photoelectron spectroscopy, when we were basically using X-rays, really high energy particles of light, to eject electrons from the atom, which end up being called photoelectrons because they were electrons that were removed by light. And back to what we were saying before about the absorption of light, this applies to molecules as well, not just atoms. And this is due to the presence of multiple atoms with overlapping energy levels. And this causes the absorption lines to be less exact and a broader peak. So instead of being like a specific line at a specific wavelength in a spectrum, we end up getting peaks. And we could see here, this is an absorbance spectrum of fuchsia dye. We could see that based off of the y-axis, which is telling us the amount of absorbance, that we're getting some peaks around, let's see, around like 550 and like maybe like 515-ish. Those are going to be the average wavelengths of absorption, but you can see that they're kind of blending together in this one big peak. But we can see two small maximums there. So it looks like there's two peaks that are blending together. So based off the fact that this is fuchsia dye, I want to know what you notice about the wavelengths that are absorbed and the wavelengths that aren't absorbed in this fuchsia dye spectrum. So think about that briefly and reflect on the electromagnetic spectrum that I showed before. I think it's on slide 14, this one. So if you look at the visible spectrum and the colors that are associated with the specific wavelengths, we can see that in the fuchsia dye spectrum that wavelengths above 600, which kind of correspond to the red here, are not absorbed at all. And then sort of below 450, we can see that they aren't really absorbed either. And we have a big absorption kind of in the middle here between 450 and 600. And if we think about the colors that are associated with those, over here is the red, over here is the blue, and the colors that are being absorbed are like the green and yellow and orange. And if we think about fuchsia is like purple. It's like a pinkish purple, which would make sense that the blue and the red are getting through the detector or getting through the atom and being transmitted and hitting the detector. If we imagine our eyes as light detectors, when we look at fuchsia dye, we see purple. And that's because we are seeing the wavelengths of light that are not being absorbed, because it's the green, orange, and yellow that are being absorbed by the dye itself. So those are basically being subtracted from the spectrum by being absorbed. And then the light that isn't getting absorbed is the light that gets through and then hits our eyes. Um, so this is true about a lot of things that are colored. We're usually seeing either light that is reflected off of that substance or light that is being transmitted by that substance. And it's usually the light that is being absorbed that we don't see. So when light is absorbed and the electrons are promoted to higher energy levels, um, they're considered to be excited electrons, but they don't stay at those energy levels forever. Eventually, they relax and they'll drop back down to a lower energy level. And they don't always drop back to the same one that they started at. Electrons are sort of interchangeable, and this causes another thing called an emission spectrum, which is kind of the opposite of an absorption spectrum. Instead, there are specific uh, wavelength that are associated with photons that are released. And this is because as an electron drops from one level to another level, it has to reduce in its energy. It has to release energy to do so. And it releases that energy usually as either a photon of light with a wavelength that is corresponding to the amount of energy differences between those two levels, or sometimes it's released as heat. But the photons that are emitted as a result of this, this process is called emission. So you have absorption and emission, which are two opposites. The absorption is the energy coming in to promote the electrons up to higher levels, and then emission is when those electrons drop down to a lower level and release a photon of light to reduce its energy. In this sense of explaining why different metals burn at different colors, this might be something you saw in a previous chemistry class, where if you take like lithium metal and strontium metal, they burn sort of a reddish color. Sodium burns orange, copper burns green, potassium burns kind of a purplish color. And this is associated with the emission of photons, because as you're heating the metal, the electrons are getting promoted to higher energy levels. They're absorbing a bunch of energy. It's not light in this case, but it's sort of the same idea. It's packets of energy that are being absorbed by the substance itself, and then those excited electrons eventually relax back down and release photons. And the photons of light are going to have colors that are associated with the energy differences of the energy shells within that specific atom. And since they all have different differences between those shells, they're all going to release different sort of photons of light. So that is it for 3.11 and 3.12. And I'll see you in the next one.